Okay, so we're going to continue our lesson on 10-1. Um, and again, there are two main focuses for this lesson. Number one is to practice eliminating the parameter for parametric equations, and the second one is to sketch graphs of parametrically defined curves. Okay, so this first example is going to have us eliminate the parameter for the parametric equations, where we have x equal to t squared plus t, and then y is equal to 2t minus 1. Okay, so I'm not going to work this one out both ways like we did the previous example. I want to eliminate the parameter in the easiest way possible. And again, for us to eliminate the parameter, we're going to have to solve for t in one of the equations and substitute for t in the other equation. So the easiest equation for us to solve for t in is the equation on the right. And when we isolate t, we're going to get y plus 1 equal to 2t. And then I can multiply both sides of that equation by 1/2, which makes t equal to 1/2 the quantity y plus 1. Okay, so once we've solved for t in one equation, we're going to substitute for t in the other equation. So when I plug the quantity 1/2 times y plus 1 in the place of t, we're going to get the quantity 1/2 times y plus 1 squared plus 1/2 times y plus 1. Okay, so we're going to go through and simplify this. I'm going to apply the exponent to both factors inside the parentheses. So 1/2 squared is 1/4. Y plus 1 squared is going to FOIL out 2y squared plus 2y plus 1 plus, and then we're going to distribute 1/2 across the next two terms inside the parentheses, giving us 1/2 y plus 1/2. So when we distribute 1/4, we get 1/4 y squared plus 1/2 y plus 1/4 plus 1/2 y plus 1/2. And then lastly, when I combine like terms, we get x equal to 1/4 y squared. 1/2 y plus 1/2 y is y, and then 1/4 plus 1/2 is 3/4. Okay, and there we have eliminated the eliminated the parameter. Okay, so moving on to the next example. Next example says for the following problems, eliminate the parameter and sketch the graph of the parametrically defined curve. Okay, so I think that looking at this example, if I were to guess on how you guys would choose to eliminate the parameter, I would guess that you would solve for t in one of the equations, substitute for t in the other equation. Okay, so if we solve for t in the equation on the left, we get x over 5 equal to the cosine of t. And then when I apply inverse cosine to both sides of the equation, that's going to give me the inverse cosine of x over 5. And then when I apply inverse cosine to the right-hand side, we have the inverse cosine of the cosine of t. And that is the composition of two inverse functions. We know f inverse composed with f and f composed with f inverse, they both cancel one another out. So that's going to give us t on the right-hand side of the equation. Okay, so we've solved for t in that equation, which means we're going to substitute for t in the other equation. So we get y equal to 2 times the sine. And then we're going to replace t with the inverse cosine of x over 5. Now, I don't know about you guys, but with this equation written in that form, I have no idea what the graph of that curve is going to look like. Okay, so we're going to use a different approach for this here. And it's going to seem a little bit tricky, but it kind of plays on some math that we've done in the past along the way in order to get into this class. Okay, so what we're going to do here is we are going to isolate our trig functions. So when I isolate my trig function in the x equation, we're going to get the cosine of t equal to x over 5. And when I isolate my trig function in the equation on the right, we get y over 2 equal to the sine of t. Now, we have looked at equations in the past that relate sine and cosine. And one of the equations that we've looked at in the past that relate sine and cosine is the Pythagorean identity, where we have the sine squared of t plus the cosine squared of t, which is equal to 1. Okay, so what I'm going to do then is I'm going to square both sides of this equation, of both of these equations. So we get the cosine squared of t equal to x over 5 squared, and then y over 2 squared is going to be equal to the sine squared of t. So using that Pythagorean identity, if we have sine squared plus cosine squared is equal to 1, that means that x over 5 quantity squared, which is x squared over 25, plus y over 2 quantity squared, which is y squared over 4, that is going to be equal to 1. And hopefully that is a more like recognizable equation for us. This is actually the equation of an ellipse, which is centered at the point 0, 0. Okay, so let's look at the parametrically defined curve in a little bit more detail, and we'll take a look at like why that graph is an ellipse. Okay, so we've eliminated the parameter here. This is our equation in terms of single equation written in terms of x and y only. What we want to do now is sketch the graph of this parametrically defined curve. So to do so, again, we're going to make ourselves an x, y, and t table. Now, as we mentioned in the last video, usually when you are graphing a parametrically defined curve, we want to pick a handful of values to find the x and y coordinates at particular t values. Okay, so I think when we look at the interval that we have in this problem from 0 to 2 pi, if I want to break that up into just like a handful of values, I think like our best incremental change for t values are going to be pi over 2, because if we break our t values up into like the subintervals of pi over 2, we're going to have t values at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, and that gives us like 5 values to test, which should give us a decent idea of what the graph of our parametrically defined curve is going to look like. Okay, so what we're going to do for these t values is we're going to plug those t values into our parametric equations. When we do so, when I plug 0 in for t in both equations, 5 times the cosine of 0 is going to make the x coordinate 5. 2 times the sine of 0 is 0, so that's going to make the y coordinate 0. When we do the same thing at pi over 2, our x coordinate is going to be 0, our y coordinate is going to be 2. When we do it at pi, our x coordinate is negative 5, our y coordinate is 0. At 3 pi over 2, our x coordinate is 0, our y coordinate is negative 2. And then at 2 pi, our x coordinate is 5, and then our y coordinate is 0. Okay, so what I can then do is make myself a coordinate plane here. And then what we're going to do is we're going to go 2 units up and down. and then we're going to go 5 units right and left. Okay, and then we're going to plot our points from our x, y, and t table. So we have the ordered pair 5, 0, 0, 2, negative 5, 0, 0, negative 2, and then back to 5, 0. And then this graph is going to look elliptical, like so. Now, our direction of motion here, are like a particle would move along this graph in a counterclockwise nature. So we're going to draw arrows indicating that. Now, beyond that, to also, because you guys are going to see, like, we'll take a look at examples that um, may go around a curve more than once or may go like back and forth along a curve. What I'm going to recommend that you guys do when sketching graphs here is to label like where a particle is going to be at certain t values. So we know at time t is equal to 0, our particle is going to be at the point 5, 0. At t is equal to pi over 2, our graph is going to be at the point 0, 2. At t is equal to pi, we're over at the point negative 5, 0. And then at t is equal to 3 pi over 2, we're at the point 0, negative 2. Lastly, we go back to our starting point at t is equal to 2 pi. Now, as far as equations of ellipses are concerned, when you look at your denominator here, the largest 0 in your denominator, when you take the square root of that number, because that value is underneath x, that tells you how far you're going to go in the x direction. Okay, so that is 5. That distance is going to be 5. Okay, and this segment here in your ellipse, that one highlighted in yellow, that is what is called the major axis. Okay, so the length of the major axis is 10. Okay, the smaller number underneath one of your variables, because that is underneath y, that tells us whenever I take the square root of that number, how far I go from the center in the y direction. Okay, so that means we're going to go up and down 2 units. Okay, so this distance here is 2. This distance here is also 2. Okay, and that segment in blue, that is what's called the minor axis, and in this case, the length of the minor axis is going to be equal to 4. Okay, so those are some things that you need to be mindful of when graphing ellipses. Okay, so we eliminated the parameter. We also did a quick sketch of the graph of that parametrically defined curve. Okay, let's take a similar example next, but we're going to tweak one thing about this example. And I want to see if you guys can figure out like how that is going to affect the graph of your parametrically defined curve. Okay, so here we have x is equal to 5 times the cosine of 3t. Y is equal to 2 times the sine of 3t. And again, we are looking at this on the closed interval from 0 to 2 pi. Okay, so I want you guys to try this one here on your own. So go ahead and pause the video, work through this one entirely on your own, and then we'll come back and work on it together. Okay, so when we look at this set of parametric equations relative to the last one, the two equations look the same. The only thing that is different is the argument of your trig function. For both trig functions in number 2, the argument of the trig function is 3t. Now, if we recall like graphing trig functions, when we multiply inside of our trig function by a number that's bigger than 1, that horizontally compresses the graph by, in this case, a factor of 3. Okay, so what does that mean? That means that your graph on the interval from 0 to 2 pi is going to have more periods than the graph will when the argument for both cosine and sine is t, like we had in the previous example. Okay, so what that means is like the graph of cosine and the graph of sine are going to repeat themselves 3 times on the interval from 0 to 2 pi. Okay, so a lot of what we do initially setting this problem up is going to be the same. So we're going to isolate the trig function once again for both of these. So we get x over 5 equal to the cosine of 3t. Y over 2 is equal to the sine of 3t. And then once again, we have the Pythagorean identity, the sine squared of something plus the cosine squared of that same something is going to be equal to 1. So when I square both sides of these equations, we get x squared over 25 equal to the cosine squared of 3t. And then y squared over 4 is equal to the sine squared of 3t. And then using that Pythagorean identity, plugging in x squared over 25 in the place of cosine squared of 3t and y squared over 4 in the place of the sine squared of 3t, we're going to get x squared over 25, plus y squared over 4 is equal to 1. So when we, excuse me, when we eliminate the parameter, we get the same equation as what we found in our previous example. Okay. However, the graph of this is going to be a little bit different. Okay. And how the graph is going to be different is like normally when we determine the period of a sine and cosine function, what we do is we set the argument equal to 2 pi. So like when we did that for our previous example, when I set t equal to 2 pi, like that tells me like how long it takes for the graph of both cosine and sine to complete one period. So for the previous example, it was 2 pi. This example is going to be different, okay, because when we set the argument of the trig functions equal to 2 pi, when we set 3t equal to 2 pi, that is going to make t equal to 2 pi over 3. Okay, so the period for both the cosine functions and the sine functions here are going to be 2 pi over 3. Okay, and that's going to affect our graph in that when we make our table, so our x, y, and t table, what we want to do is we want to break the interval from 0 to 2 pi to 2 pi over 3 up incrementally. Okay, and then if we're going to pick like a handful of t values, I'm going to take this and multiply it by 1/4. When I do so, I get 2 pi over 12, which is going to be pi over 6. And that's going to be how I break like my t values up into equal subintervals. So I'm going to start at 0, and then each incremental change for my t values are going to be pi over 6. So the next entry is pi over 6. If I add pi over 6 to that, we get 2 pi over 6, which is pi over 3. If I add pi over 6 to that, we get 3 pi over 6, which is pi over 2. If I add pi over 6 to that, we get 4 pi over 6, which is 2 pi over 3. And that completes one period for both the sine and cosine graphs. Okay, now when I evaluate the parametric equations at those t values, we want to find the corresponding x and y points on the graph of our curve. Okay, so when we plug 0 in the place of t into both of our parametric equations, the x coordinate at that t value is 5, the y coordinate is going to be 0. When we do the same thing at pi over 6, x coordinate is 0 and the y coordinate is 2. When I do it at pi over 3, x coordinate is -5, the y coordinate is 0. At pi over 2, the x coordinate is 0, the y coordinate is -2. And when we do the same thing at 2 pi over 3, x coordinate is 5 and the y coordinate is 0. Okay, so let's make ourselves a coordinate plane here to sketch our curve. We're going to go up and down 2 units again. We're going to go right and left 5 units. Okay, so we're going to mark our points along the graph. So we are going to start at time t is equal to 0 at the point 5, 0. So I'm going to label like the t value here that's at 0. Then at pi over 6 at t is equal to pi over 6. We are up at the point 0, 2. At pi over 3. Sorry, let me move this over here. So at pi over 3, we're at the point -5, 0. At t is equal to pi over 2, we're at the point 0, -2. And at t is equal to 2 pi over 3, we're back at the point 5, 0. And again, we know that the graph of this curve here is elliptical, so I'm just going to draw an ellipse. Passing through those 4 points. Like so. Okay, and the direction of motion here, once again, is going to be clockwise. Now, what's going to be different here about graphing these sets of parametric equations, or this set of parametric equations, is like when a particle moves along this ellipse, it's actually going to circle the ellipse 3 times. How do I know that? Well, if we keep adding our incremental change of pi over 6, so starting over here at this point right here that I highlighted in yellow, so going from 2 pi over 3, if I keep adding pi over 6 every single time I make a movement around the ellipse, 2 pi over 3 is 4 pi over 6 plus pi over 6. So is going to put me up on the positive y-axis at 5 pi over 6. When I add pi over 6 again, that's 6 pi over 6, which is pi. That's going to put me on the negative x-axis. When I add pi over 6 to that, that's 7 pi over 6, which is going to put me on the negative y-axis. When I add pi over 6 to that, that is 8 pi over 6, which is 4 pi over 3. That puts me back on the positive x-axis. If I add pi over 6 again, we get 9 pi over 6, which is 3 pi over 2. That puts me on the positive y-axis. When I add pi over 6 again, that's 10 pi over 6, which is 5 pi over 3. That puts me on the negative x-axis. When I add it again, that's 10 pi over 6 plus pi over 6 is 11 pi over 6. Puts me on the negative y-axis. And when I add pi over 6 1 last time, 11 pi over 6 plus pi over 6 is 12 pi over 6, which is 2 pi. That puts me back on the positive x-axis. So we actually see that like we had a particle that was moving along the ellipse, that's going to circle the ellipse 3 different times. Okay, which makes sense because by changing the argument of cosine and sine to be 3t, that horizontally compresses the both of those functions, which means they have more periods. They actually have 3 times the amount of periods as the previous functions did in the previous example, which is going to mean that graph circles the curve more times. Okay, now if you blindly didn't take into account the fact that the period is going to change, and you would have did what you did in the previous example where you took the interval from 0 to 2 pi and broke it up like so. So 0 pi over 2 pi, 3 pi over 2, and 2 pi. You're going to get misled because starting at 0, your particle is starting on the positive x-axis. If you look next at pi over 2, that's on the negative y-axis. The value of pi is on the negative x-axis. The value of 3 pi over 2 is on the positive y-axis. So if you didn't adjust the t values that you were testing based on what the period of the function is, just looking at where those values that I highlighted in blue were on the graph, it would look like, and sorry, I realized I screwed this arrow up. This arrow should be going in this direction here. But it would look like a particle would be moving clockwise along that ellipse, which is erroneous. Okay, because again, when you look at 0 pi over 2 pi, 3 pi over 2, it looks like particles move clockwise along that graph. That's not the case. Okay, graphs move, the particle would move counterclockwise along this graph based on the period of both the cosine and sine functions being affected. Okay, so let's move on to this example here. Again, I want you guys to give this one a try. So you have x is equal to the sine squared of t, y is equal to 2 times the cosine of t. You're looking at that on the interval from 0 to 2 pi. Okay, so I want you to eliminate the parameter and sketch the graph for that parametrically defined curve. So go ahead and pause the video to do that. Okay, so let's take a look at this one. Again, some similarities to the last one. Just going to be a slightly different problem because x is defined as the sine squared of t. Y is 2 cosine of t. So I'm going to do the same thing that we did in the previous 2 examples. When I isolate the trig function, y over 2 is equal to the cosine of t. And then when we square both sides, we get y squared over 4 equal to the cosine squared of t. So again, if we use the Pythagorean identity, sine squared of t plus cosine squared of t is equal to 1, that would give me the equation. So sine squared is equal to x, cosine squared is y squared over 4 is equal to 1. And when I isolate x, we get x equal to 1 minus y squared over 4. Okay, so we have x equal to some negative y squared. That's going to be a parabola that opens to the left. But let's confirm that. So again, this is our equation where we've eliminated the parameter. Let's go ahead and sketch a graph of this. So we're going to make ourselves an XYT table over here on the right. The arguments for both trig functions are t, so I don't have to do anything as far as period is concerned. So I'm going to pick a handful of values. So if I break the interval from 0 to 2 pi up into subintervals of length pi over 2, that's going to make our t value 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then we want to find the ordered pairs that correspond to each of those t values. So when we plug 0 in the place of t for both equations, sine squared of 0 is 0. 2 cosine of 0 is going to be 2. When we plug pi over 2 in, sine squared of pi over 2 is 1. 2 cosine of pi over 2 is 0. When we plug in pi, we're going to get coordinates 0, negative 2. When I plug in 3 pi over 2, we get coordinates 1, 0. And then when we plug in 2 pi, we get coordinates 0 and 2. Okay, so we can go ahead and make ourselves a coordinate plane here. I think that this is going to be enough. So if I make a coordinate plane going, let's say, 2 units in each direction. So we're going to go up 2 units, down 2 units, right and left 2 units. Again, we know that this is going to be a parabola opening to the left. So we're going to go ahead and start by plotting our points. So we have one at 0, 2. So our graph is up here at time t is equal to 0. Then we move to the ordered pair 1, 0. We are there at time t is equal to pi over 2. We're down here at the point 0, negative 2 at t is equal to pi. We're back up to the point 1, 0 at t is equal to 3 pi over 2. And then we're back to our starting point at time t is equal to 2 pi. So our parabola opening to the left graphically is going to look like so. And then we want to draw arrows indicating direction of motion. So we're going to start out moving down and to the right. We're going to pass through that x-intercept, and then graph is going to continue moving down to the left. We're going to hit that point 0, negative 2 at t is equal to pi, and then our graph is going to bounce back and then work our way up and to the right, passing through that x-intercept and working up and to the left. Now, if we just have the arrows only, like it's not clear, like when is our particle moving like clockwise, when is it moving counterclockwise. So this is why I like labeling the t values, because it makes it super clear as far as like when we look at the t values, like in what direction our particle is moving at various instances of time. Okay, so that would be the graph of that parametrically defined curve, okay, where we start out moving clockwise, and then our graph is going to bounce back and move counterclockwise along that parabola. Okay, so last example, we're actually not going to do on this video. I'm going to work this example out for you guys in class. I don't know how to display on my screencast like my normal laptop screen, and I have my graphing calculator on my laptop. So I will show you guys how to do this next one in class, but I want you to get the problem copied down, so it's just really easy for you guys to go in and fill this example out in your notebook. So directions here say, how would you use a graphing device to sketch the following curve? Okay, so we have the equation x is equal to y to the 4th power minus 3y squared. And we're going to talk about in class how we would use our graphing calculator to graph that curve. Okay, so that'll be it for this lesson on 10-1. And hopefully I'm back at school on Friday to continue our lesson. I will post a video um, for 10-2, but I will do that later on this evening sometime. So make sure you guys watch that video from 10-2 so we can pick up from that point in class next time. All right, guys, have a great rest of your day. See ya.